While many experimental techniques can be used to characterize the transition from an ordered structure to a disordered one of these techniques, namely the differential scanning calorimetry, takes center stage in a course on thermodynamics. Differential scanning calorimetry provides a wealth of thermodynamic information about both the substance investigated and the order-disorder transitions. Quantities such as the constant pressure molar heat capacity of the substance in both the low temperature ordered phase and the high temperature disordered phase, the transition temperature and enthalpy change. Information about the transition temperature and enthalpy change can inform a discussion of the change in intermolecular interactions as a result of the transition and help model the mechanism of disordering, thereby shining useful light on the folded or native structure of a protein, for instance. How are differential scanning calorimetry, or in short DSC experiments, carried out? There are a variety of DSC instruments on the market. So I will focus on a fairly common one here, the power compensated DSC. Such a DSC contains two small chambers, one for the sample you wish to study, the other, usually empty, is called the reference. Each chamber is equipped with its own heater and thermometer. In a typical experiment, a sample and the reference are heated at a constant heating rate in degrees Celsius per minute, and the difference in heating power between the sample and the reference is recorded as a function of the temperature in the sample and reference. There is always a difference in the power needed to heat the sample and the reference because on the reference side we have an empty container, while on the sample side we have a container and a sample. In the absence of phase change, difference in power allows to measure the constant pressure molar heat capacity of a sample. If we were studying what happens during the heating of a sample of a protein called Barnase, we would be able to measure the constant pressure molar heat capacity of the Barnase protein in the native state at low temperature, and we would find a value of 15 to 20 kJ per mole per Kelvin. We would also be able to conclude that this protein has a molar heat capacity at constant pressure of about 27 kJ per mole at temperatures of 90 to 100 degrees Celsius, when it is in the denatured state. Looking at the DSC scan of the Barnase protein, in the temperature range between 60 and 90 degrees C, we observe a large peak. What is this peak due to? First, we note that because the peak is pointing upward, it corresponds to an absorption of thermal energy. Its area can actually be related to the energy change, same as enthalpy change for non-gaseous systems, associated with the unfolding process. Examination of the DSC peak allows us to conclude that the largest amount of energy released per unit time occurs when the temperature is about 73 degrees Celsius. This temperature will be called the denaturation or melting temperature of the Barnase protein.